We're going to have instruction on waves in general today, and actually a little bit of electromagnetism, which formally is a topic in Physics 2054, but we'll just do some basics about electromagnetic waves. I'll talk about some recent news from the world of paleontology, and then hopefully interference and superposition. Now, if we don't get to that today, we'll do that on Monday. That's the back chapters of chapter 16. Written homework 8 I'll be publishing tonight. In case I don't get down to the very end of the lecture, let me just let you know that written homework 8 is going to be an oscillator problem, and it's going to be about dissipating energy in a damped oscillator. And I'll set it up so that you can do it without having to be an expert in calculus, which, damped oscillators, to really understand and take it apart, you have to analyze it with calculus. But also, I'm going to be giving double points today for clicking because it's a Friday on a nice day. So everybody that's here clicking today, those people, look at all the empty seats. It's too bad. All right, let's proceed. We're going to talk about waves. Let's get down to some of the basic concepts. This is one of my favorite photographs. Here's probably, to me, the most important concept about waves. They transport energy and momentum from point A to point B in space-time. A wave in the ocean does not transport water necessarily. Now, when you're at the beach, of course, the water's actually moving. But when you're out there in the middle of the ocean, you see a wave coming ashore in Cocoa Beach from the southeast. That means it came from some storm off the coast of West Africa, maybe. But that's not water from West Africa that's forming breakers at Cocoa Beach. It's the Gulf Stream came out of the Gulf of Mexico. All right, but the energy from that storm was transported through the phenomenon of waves. One of the most important principles is that they're not easily localized. You think about, most of the things that we started off with this semester, like a baseball, an apple falling out of a tree, a boxcar, blah-de-blah. Those things can be approximated as a point mass, and that's why in a free body diagram we use a dot to represent that mass. And usually the location of that dot formally should be the center of mass of the object, and then you track the center of mass. And for a rigid object, at least as rigid as a human being, that's perfectly fine. It works out nicely. And then you abstract it down to a point particle, like a little miniature BB with a certain mass, certain velocity, and then you figure out using F equals ma where it's going to go. That's not possible with waves. What is the mass of a wave? Look at this. I mean, this disturbance, you're looking at a pond or a creek that's flat, and you drop a stone in it, and the waves go out in circular pattern like that. What do you weigh? What do you take the mass of? How deep do you have to go? If you say, well, I'll just take the first 7 centimeters radius around where the rock went in, okay, good, that's nice. But those waves are going to soon be past the 7 centimeter mark, right? So then what do you do? And then, and while they're racing across the pond or the creek or the swimming pool or the bathtub, wherever you're doing this, they're racing past the 7 centimeter mark. The interior 7 centimeters might damp down to zip-zap. In other words, flat water. So then what do? All right, so waves they're definitely different from Newtonian particles, right? So, and for instance, when a wave comes to a barrier and goes around the end of it or through a gap like this, right? It forms wavelets at the gap or at the edge. Now these waves are coming in from below, and they're marching in like, like sometimes you see out at the beach, the waves are just coming in nice and uniform, nice and straight, and they're coming in from a certain direction. And these ones are coming in from below. Now this is a picture of something that is called a wave tank. And a wave tank, have you guys done wave tanks up there? Waves or anything in lab? Okay. A wave tank is a big, you know what it's like? It's like a really shallow swimming pool with a glass bottom. And it's up on stilts. So you've got this glass bottom and maybe a couple inches of water in it. And then it's up on a stand, maybe a foot or two. And then underneath it, you put a piece of blank white paper. Or if you have a white tabletop, that works as well. And then from above, you take, one of these little things, the lab brackets, and you suspend a light from above it so light's shining through it. And then you start disturbing the water. And the pattern of shadow and light on the tabletop from the light suspended above shining through the water where the water waves are leaves an image, and that's what this is. This is an image from below a wave tank of wavelets being formed here in the gap. So right here in the gap, the waves don't go straight through. It's like they start it's like somebody's dropping little teeny stones in the water there. And they form little teeny circles of waves going outward, and they keep going outward, and by the time they escape from the gap, they're curving around like this. See, these ones are flat down here. The incoming waves, these are what we call plane waves, all right? But these ones are not plane waves anymore, right? And you can see that there's a really strong set of waves right down the middle here. Okay, that's called the central maximum. But then over here, right about here, you got another set of waves, and they're not nearly as strong, but you could definitely see them. The same tilt angle over here to the right, you can see them. Those are called diffractions. Okay, this is the 0th order diffraction here in the middle, the bright one, or the strong one. And then this is like m equals 1, and then this one down here would be m equals 2. And then you have m equals 1 and m equals 2 over here. Okay, that's diffraction. So particles never do that. All right? But waves do it out the wazoo. Now, by the time you're at the end of 2054, you're going to be ready to tackle the periodic table. And you may even, if you have a good instructor, you might be able to attack the periodic table. The wave nature of matter, electrons, protons, the neutrons, and so on, is essential. And diffraction is essential for understanding the periodic table, in general, interference itself. So here's a Newtonian particle, this red one. I can just go ahead and look at the animation. You know what a Newtonian particle will do? It won't form wavelets. What it will do is it'll get to the barrier and then it'll go straight through. Or if it's off to the side, it'll hit the barrier and then bounce back, but it won't diffract. So if you're recording the impact of Newtonian particles, you'll have a lot of scores here, but you won't have jack to the left and right. But with waves, you're going to get a lot of wave energy to the left and to the right, alternating with zones without wave energy. That's the dark part of a diffraction gradient. And the first day of lecture, we looked at the spectral fingerprints, the quantum fingerprints of hydrogen. And we saw red light diffracted way out to the side, and the two purpley blue ones deflected. We saw the central image, And we saw the purpley blue ones deflected a little bit to the left or to the right, and then kind of an aqua bluish one, and then a bright red H alpha way off to the right. That's diffraction, right? And every wavelength for a given gap like this, 7 centimeters or 7 nanometers, the different wavelengths will behave differently. Some will diffract like crazy, some will just go charging through as if they're particles. So, now another thing about waves, they have a fairly simple wave equation, V equals lambda F. All right, now let's talk about the specs for that equation. Wavelength is lambda. Now that's the distance between two successive waves. So peak to peak or trough to trough is a good way to think about the wavelength. Now that's a spatial distance. Waves in the ocean, you're probably talking a wavelength measured in meters. And a period measured in seconds. Okay, or maybe, I'd say seconds, tens of seconds. But wavelength in meter, but for things, like light, you're talking nanometers for the wavelength. Period T, that's the temporal interval between waves. So you're sitting out there on the end of the jetty, and you're watching the waves come in, and you're just dreaming about how life is great, or whatever you're thinking about, the price of tomatoes in China or what have you. And you notice that the waves come in every 6.5 seconds. And you go another 6.5 seconds, and another wave crashes on the jetty. Another 6.5 seconds, another one crashes on the jetty. Or whatever the time interval is, that's the period. Now the frequency is 1 over that, right? And I think we've talked about this many a time already. So every wave phenomena that we see in nature usually has a wave formula, something like this. And the most complicated wave equation I've ever seen was a wave equation that expressed waves in the plasma on the surface of the sun, which is a fluid of charged particles, very high energy, because the surface of the sun is very hot. And they're bound by gravity, but they're also convecting, and they're also trying to escape, and they're electromagnetic. So the electrons are separated from the positive ions, the hydrogen nucleus, the hydrogen nuclei, and the alpha, the helium nuclei. And so what the positives do, the electrons do the exact opposite. So it's this roiling, boiling maelstrom on the surface of the SUN, 5,800 degrees Kelvin scale, but it has a wave equation, and you can make out the same structure. I mean, there's all kinds of factors of density and velocity and, elevation, and even the angle and stuff. But it all boils down to something that looks an awful lot like V equals lambda F. You can see it. But it's very complicated. So now let's talk about light itself. It's a wave in the electromagnetic field. And you'll learn more about the electromagnetic field when you start 2054. It affects compasses and electrons and protons. Electrons and protons, negative charges for electrons and positive charge for the proton. And the electromagnetic field also affects compasses, needles, magnets. So that needle will, swing one way or the other depending on the electromagnetic field, if there is one present. All right. Now, it forms a spectrum. And in reality, sound has a spectrum as well, sound waves. Sound waves in air, we go, like an A is like 110 hertz is the frequency. Is that right? Does anybody know their musical scales? Good. 110 hertz. Is that, or is it 210? I think it's either 110 or 210.
What's the question?
For an A, a note. The A note. So not A sharp, not A flat, but A. I think it's 110 hertz. And so, but the next octave above that's going to have a higher frequency and a different wavelength in air. And that's why, the piano has that unusual curved shape. It has some long strings down in the low notes and some really short strings in the high notes. And so one side of the piano, the right side, if you're looking at it, is fairly short, and the bass side, the left side of the piano's got those really long strings. So all that's a spectrum as well in sound waves. For electromagnetism, it's, you can break it down into wavelengths as well. Question, Brandon.
Middle C is 440 hertz.
A above middle C?
440.
A above middle C is 440 hertz. So, but I think there's an A lower than that, maybe that's 110. Yeah, down an octave or two. I'm not sure. I'm like the world's worst musician. But anyways, if you break it down in the electromagnetic spectrum, you have small wavelength gamma rays, large wavelength radio waves, and stuff in between. Now, visible is considered the middle, and that's red-orange. That's Roy G. Biv. Okay, so you have radio, you have infrared, you have visible light, Roy G. Biv. And Roy G. Biv is the name of a famous scientist that just happened to have the spelling of his name exactly the order of the colors in the visible part of the spectrum. I just saw a student go over here as soon as I said that. She gave me the eyebrow up, like Mr. Spock or in Star Trek, oh yeah, right, Dr. B. Yeah, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. This is a good way to remember the colors. And then above Roy G. Biv is ultraviolet. Below it is infrared, even redder than the reddest red that you can imagine. Ultraviolet, even more purpley than the most purpley purple violet that you can imagine. And then X-rays and gamma rays, all right? And the speed of light in the wave equation, the speed of light, the wave equation is c equals lambda f. It's 3 times 10 to the 8 meters per second. And so that's pretty fast. In 1 second, 300 million meters of travel for, so 1 second in the past is farther away from you than any point on Earth. So that's why the past is so difficult for us. So here's the same chart. Now, over here, the gamma rays, go ahead and make a note, shorter wavelength, larger frequency. And the larger the frequency, as you'll learn in Physics 3 if you take it, the photon has larger energy. The photon energy is proportional to the frequency. Over here on the long wavelength end, you have longer wavelengths, so smaller frequency. And each photon in that regime is smaller energy. And then Roy G. Biv's kind of in the middle. Now, a couple things about this. There's no hard and fast boundary lines for radio waves and infrared and violet stuff, gamma rays versus X-rays, ultraviolet versus X-rays. But here's, down here in the millimeter range, you'll hear people talking about microwaves in the millimeter band, or you'll also hear them talking about radar waves, like a millimeter radar, search radar, or tracking radar. So if you're in the Navy, has anybody in here ever been in the Navy? Yeah, I got friends that are in the Navy, out on these destroyers, these Aegis class destroyers and cruisers. And they got all those radars on there. They're looking at every doggone thing that they can see. They're tracking it all, baby. And so they got millimeter radars, centimeter radars, So radar is going to be, in the millimeter and centimeter band. And one man's infrared might be another man's microwave. So, so in other words, an engineer might refer to something as infrared, and a different engineer might refer to the same wavelength and frequency as microwave. All right? So, there's a lot of leeway. The rough rule of hand for the visible Roy G. Biv band is 400 nanometers to 700 nanometers. So violet is the 400 nanometer end, and red is the 700 nanometer end. Now here's something that's interesting. I sometimes discuss this, and I'll discuss it with you students. When you're in art class, you think of colors as a wheel. You know, you go from violet to blue, indigo. No, violet to indigo to blue to green to yellow to orange to red, and then back to violet, right? It's like a circle, color circle. But that's not what nature is. You know, if you think you're going to get back to a purple up here at 800 nanometers, no way. It just keeps going. So that's why I always say these colors out here, if you could see them, would be processed in your brain as the reddest red, redder than the reddest red that you've ever seen. The same thing on this end. The violet end, the short wave, 300 nanometers, officially that's ultraviolet. If you could see it, that would be more purpley than the purplest purple that you've ever seen. Okay, because that's the direction that the true colors go, in that direction. They don't form a wheel, except in art class. And that, there's usefulness for that color wheel. But, not in terms of physics. Question?
Just out of curiosity, would X-rays and gamma rays be just like super, super deep purple too?
Yeah, I mean, you could think of them as ultra deep purple. So purple you can't even think about it. So purple it gives you a headache to think about it. So yeah, I mean, and radio waves are so red that it blinds your eyeballs. So now the wave equation for light in this spectrum, c equals lambda f. So the special symbol that we use for the velocity of light is c. And we've already mentioned it, c equals 3 times 10 to the 8 meters per second. This is the famous E equals mc squared symbol, c, the speed of light. And so, yeah, we're going to use this here. I'll get your clickers out. We're going to do a little bit of practice with c equals lambda f here. But first we'll do a practice calculation, and then I'll let you guys do a calculation. All right? So here's our wave equation, c equals lambda f. All right? And so wavelength times frequency is the speed of light. Speed of light is a constant. Wavelength is spatial, so it's going to be measured in centimeters or meters or kilometers or something like that, nanometers for visible light. Period is temporal, so that's seconds, or microseconds or nanoseconds. Frequency is 1 over that. So the unit of frequency per second, or hertz, as we know. And of course, here's a picture of Professor Hertz. He's the first scientist to actually, so they came up with the theory of electromagnetic waves, and then he said, let me see if I could build a device to generate electromagnetic waves and verify at a distance, 10 feet away or 20 feet away or something like that. He was the first guy to deduce that. Now we're going to do a little exercise here. Just to remind you, the metric prefix is nano means 10 to the minus 9, and tera means 10 to the 12. So we're going to have some terahertz frequencies here. So just make a note, terahertz means 10 to the 12 regular hertz. All right? Now we're going to calculate the frequency for H alpha, the red color that we saw coming from hydrogen on class in lecture 1. Okay, and we know, in the laboratory, if you do your diffraction grading in a set location, a set distance away from an observing screen, and then you do all the trig and stuff, you can work out pretty carefully, pretty well, the wavelength. And then you do this calculation to figure out the frequency. So you take the wave equation, and then what you do is you say, all right, I want to get the frequency, so let me divide both sides by lambda, and I get c over lambda equals frequency. All right. Now, if you want to figure out lambda, if you're given, like the frequency of an FM radio station, and you want to figure out the wavelength of it, then you would whoops, you would use this formula, C over whatever frequency you're given equals lambda. So you can use this wave equation either way, right? Now your written homework is not going to be involved with this, but you may find on the final a simple calculation or two of either frequency or wavelength. So let's do the frequency here. C over lambda equals frequency. So there's my numerator, 3 times 10 to the 8 meters per second. Good. And notice that I'm kind of cheating with my scientific notation. That should be 6.56 times 10 to some power. But since I'm lazy and since my calculator can handle it, I can type it in as 656 times 10 to the minus 9. Or, if I'm really, I could cancel meters here. And this per second in the numerator doesn't cancel, so it persists. And that's going to be my hertz for my frequency. So that's good. All right. So if you're lazy, you're doing it on paper, you forgot your calculator, you could do it this way. Take the 3 and the 656 and kind of park them out here to the left, and then take this 10 to the minus 9 from the denominator and bump it up to the top, and so you have a total of 10 to the 17 on top, and then your hertz out there to the right. So on a calculator, you would type it in like this: 3 EE17, and then the divide by sign, and then 656. Or you could just do this one over here straight if you know what you're doing. And I highly recommend that you get familiar with your scientific notation on your calculator. And by the way, on the final, you will not be allowed to use your cell phone, so it behooves you to get a calculator. And even a cheap $15 special from the bookstore will do. All right, so you do this calculation, 3EE17 divided by 656, and you get 4.57 times 10 to the 14. Now, I'm going to ask, when you guys do your calculation here in about 2 seconds, I'm going to ask you for an answer in terahertz. All right? Now, this is 10 to the 14, not 10 to the 12. So you got to factor out the terahertz, and the answer here is 457 terahertz. Now, if you got tripped up on that, or if you're wondering, Dr. B, how did you get 457 out of that? Well, let's take a look at it. You take the 457 and the 10 to the 14, okay, that's down here, and then you say to yourself, all right, that 10 to the 14 is the same as 10 to the second times 10 to the 12th. All right, now that 10 to the 12th is terahertz territory. All right, so that's good. But then I got to multiply 10 to the second by 4.57, and that's this. And so that becomes 457. And then this one over here becomes terahertz. Okay, that's how you do it. All right? Now let me pause for questions, because you're about to do some clicking questions. You're going to have a multiple choice first, and then you're going to have a calculation second. You're going to actually calculate it and give me some terahertz. So you're going to have to know how to do this.
Like a numerical.
Yeah, you're going to have first question is going to be multiple choice. Second is going to be numeric. Questions? Yes? Yeah, the reason I do that is because on clicking and in web courses, I have to specify a whole number or maybe a decimal and the units to report it in. You know how I always say, for instance, if your answer is something, point something, round it off to the nearest 0.01. Okay, now in this one, we round it off to the nearest terahertz. But if I was given a written exam, this up here would be lovely. In yellow, that'd be perfect. I'd look at that and say, all right, they got it. But if I'm using a clicker or a Scantron, well, I can't do Scantron, but or web courses, you got to, I don't want you to type in scientific notation on web courses or the clicker, because that's a recipe for misfire. So I give you the basic, I give you the exponent.
I'm sorry, I don't have any places to show.
Siri, you're very enthusiastic. So, you know, I got to give you, so basically what I'm doing is giving you 10 to the whatever power and then asking you to, you know. All right, so here we go. Another question. All right, let me turn on my rig. All right. And the first question is kind of a visual perception test. Multiple choice. How many waves, including fractions of a wave? So you might have something 0.50 or something 0.00. So just kind of eyeball that real carefully. And remember, a full wavelength is peak to peak or trough to trough, or 0 point to the next 0 point of the same kind. So A and B are 0 points, but they're not the same kind. One's ascending, the other one's descending. 20 seconds starting now. Ten, 9, 8, 7, 6, 5, double points, 3, 2, 1. So we have just a little bit more than half the class. Good, you guys are good and faithful students. You're getting bonus points today. Let's take a look. All right, here's a wavelength. See the red arrow there? All right. So now let me put that down here at A. All right, so that's one wavelength. So I got at least one. And then here's another one, so that's 2. And then that last bump, that's a half a wavelength. So my answer is 2.50. Raise your hand if you voted for 2.50. Good. All right, now the rest of you, keep that in mind. All right, do not let me catch you. Well, it's not that big of a deal. I saw a guy over here in the middle going, oh yeah. You know, like oh yeah, I just won the lottery and the Super Bowl, yeah. Yeah, well, it is double points, sure. So, anyway, so one bump, like this last one, is a half a wavelength, so we got 2.5. And counting fractions of a wave is important, you know, because you know you can have 2 waves that are in phase or out of. If they're out of phase by half a wavelength, that means they're perfectly out of phase. You have a bump corresponding to a dip. Okay, hit the refresh key. And let's do a numeric problem. Hold on. Okay, now this is the purpley H delta line that we saw on the first day of classes. And go ahead and start with that. Hit the refresh key. Remember to hit the send key. And this is going to be a number of terahertz. And that big ginormous number, 123099844, that's just me typing in digits. That's 10 to the 12 of something, or 100 times 10 to the 12 of something, and then, but you round it off to 123 terahertz. All right? So take a few minutes to do that. Consult with your neighbor, as always. Consult with your mind. Consult with your notes. Let me see what you guys are voting for. Be careful with your rounding off. And make sure, give it a try with scientific notation on your calculator. What's that? Just round to the nearest terahertz. Okay? So whether it's rounding down or rounding up, just depends on what that last significant figure is. Mariana. Where's Kara? Okay. All right. I see you guys voting and stuff. Good. All right. 1 minute starting right this second. 1 minute. Don't type in 123. That's a fake answer. Try to get your answers right. Do them right now, and then you'll be ready for the final. Ten. No, sorry. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hurry up. 0. Okay. Slackers. They didn't get it. Don't forget to, hey, everybody hit your send key. Don't forget that. Okay, now we got it. 144. All right, raise your hand if you typed in 732. Sweet. Good, yeah, that's the answer. Now, all right, let's just double check it. In case you got tripped up, here's your calculation. Speed of light divided by the wavelength. And this one's 400 times 10 to the minus 9. This is H delta. The purpley line, the closest purpley line in the visible wavelengths of hydrogen. 410 times 10 to the minus 9 meters, 3 times 10 to the 8 meters on top. Meters cancel, of course. You're left with hertz. So your lazy bones, no calculator method, 3 over 410 times 10 to the 17, which would be 3e17 divided by 410. Or you could just go straight like this. I mean, here's the alternate version. 3ee8 divided by 410ee, then change the sign key, and then a 9. That'll give you 410 times 10 to the minus 9. And in both cases, you should get 7.317 times 10 to the 14 per second, which is then 732 terahertz. All right? Now, I want to talk about, so you guys did good on that. You got like 80% if you got it right. I want to take a few minutes in the way of giving you a real-life explanation about why waves are important. We recently had a geological discovery published in the past week about a geologist up in Montana and North Dakota who discovered a fossil-bearing formation that's related to this asteroid impact in the Yucatan, the Chicxulub impact, that they think extinguished all the dinosaurs. So it was down in the Yucatan, roughly in this position here. They think that it left a crater like that. Now, here's the overhead view. This one shows a lot of the water features. These little blue, pale blue features are, I think they're like water, they're like these circular pits that are filled with water, weakness in the limestone or something like that. But they formed this ring, and that's one of the ways that they found it. They were looking for petroleum. This is a gravity anomaly. So in other words, measuring where gravity is a little bit stronger or a little bit weaker than 9.8000. They found the impact crater. They didn't know what it was. They found this ring-shaped structure down in the 70s when they were prospecting for oil, for petroleum. And then in the 90s, they kept going back, and they recovered what we call impact glass. Now, impact glass, when the asteroid impacts, it melts the rock. The rock goes flying into space, and some of it comes down close, some of it goes thousands of miles away. But it cools down so quickly. If it's an igneous rock, it'll form a kind of a glass, right? Because all this stuff there's a lot of silicon and oxygen. Silicon dioxide is sand, and that's what glass is made of. So they found the impact glass in this formation, and so somebody said, you know what that is? It's not some weird geological formation. It's an impact crater from an asteroid. So then they figured, okay, this must be the reason. They figured out the age of it, and they figured out, okay, this might be the reason that all the dinosaurs got greased about 65 million years ago, except for Barney. Now this guy, he's the guy that figured out, that discovered this formation, is actually a grad student at University of Kansas. And so this is a newspaper article from the Kansas City Star. Here's the bit.ly address for you if you want to jot that down. I'll put it in additional readings. And where they found this fossil-bearing formation, they found a lot. What they found was they're digging, out there in this part of Montana. It's called Hell Creek, out in the Montana-North Dakota boundary. They find a lot of, Jurassic Park, where they're out there in the arid area and they're digging for fossils and stuff. That's a real place. That's a real place in Montana. And this is one of them, Hell Creek. All kinds of fossil-bearing formations out there, yeah.
That article was posted April Fool's Day.
Yeah? So?
Is it legit?
It is legit. Yeah, you can read there's a technical article from Proceedings of the National Academy of Sciences. I'm in the middle of reading it. Yeah, it's legit.
Just a bad day to place.
It's a bad day. Yeah, it's a bad day for Montana. So what they found, so they're looking at these, they're looking for Triceratops. And one of my friends from Montana, he's actually been to Hell Creek, and he's trying to unearth some Triceratops skulls out there that he's got scouted out. Anyways, so this one formation, it had buku fish, and these are sturgeon and gar, which sturgeon are these gigantic fish that live in big rivers and lakes, and they feed by sucking stuff through their mouth and into their gills, and their gills strain out their food. So what they found was these fish were all dead, piles of them, all aimed the same direction. And in their gills were these tektites of impact glass, and they analyzed the chemistry of it, and they figured out that this is the same kind of impact glass as the Chicxulub impact. The interesting thing, they were also mixed in with continental land animals, so dinosaurs and stuff. But here's the interesting part. Back in those days, North America had an inland sea. So Montana, where they found this, was a bay and then a river at the top of the bay, right? And so where the Great Plains are now, that was a big, what they call the Western Inland Sea. Now, here's the impact down here in the Yucatan. And up there, the black circle up here in Montana, that's 1,900 miles. All right? They worked out the physics, and they figured out that these animals died less than an hour after impact, about 1,900 miles away. So they've got a snapshot of the bad day, the day that the dinosaurs got extinguished. And what happened was a seiche, S-E-I-C-H-E. It's a new term to me this week. Formed in Montana from the Yucatan impact. Now, basically what you can say is the Chicxulub impact rang the earth like a bell. And the seismic waves went out all through the earth and basically caused a monstrous storm surge, like a storm surge, except it wasn't weather-based, it was seismically based. Now here's what a seiche looks like on Lake Erie. Does that look like a wave or what? Look at this. Let's look at this inner area here closely. This is the water level versus the average water level, and it's going up about 8 feet. Now let's look at this up close. The red part, the upper curve, is the water level in Buffalo. This is formed from atmospheric storms. The blue part is Toledo. Let me go back to that. The blue part is Toledo, and then Cleveland's kind of in the middle there, the green. Now Toledo's at the opposite end of the lake. Here's Lake Erie. Buffalo is up here. And Cleveland's down here kind of 2/3 of the way to Toledo. Toledo's over here. So that's about 400 kilometers. So look at that. You've got a peak and a trough separated by 400 kilometers. Think of the wavelength of that wave. Now that's what happened in Montana. Within minutes, for a seismic wave to travel 1,900 miles, that's a couple minutes. So that bunch of dead fish and stuff, and you know what else they found? They found the tektites, the little spheres of impact glass, the ones that really go far. They found them in the gills of these fish. They also found it embedded in amber, which is pine sap that then, the pine tree falls and becomes fossilized, and that's how we get the mineral amber. And just like in Jurassic Park, they found a mosquito embedded in amber, and they extracted the DNA of dinosaurs because the mosquito bit a dinosaur, and then they made the T-Rex and velociraptors and stuff. So this one, they got tektites from Chicxulub. 2-3 minutes later, embedded in the amber and in the gills of those fishes. Can you imagine? Talk about a bad day. Now, what causes a seiche to form in a river or a bay? Interference. We'll talk about it on Monday. You're dismissed. Look for the homework tonight in web courses.